Hello everyone. Today we will show you why we need a voltage regulator. Okay. How a Zener diode will act as a voltage regulator. Suppose we have a voltage source. Okay. That voltage source is 20 volt, and we all know that the internal resistance of the voltage source should be 0 ohm, right? But we assume that the internal resistance of this voltage source is 1 kilo ohm. Okay. And we connect a resistance of 1 kilo ohm as a load. Okay. So suppose you bought a voltage source, so what do you expect? You expect that you will connect any resistance with that one and you should get the same voltage at the output, right? Here the voltage is connected is 20 volt, right? So we should get in the output is 20 volt. But what we will get? If we simulate this circuit, you can see we get only 10 volt. Why? There is some voltage drop across the input resistance of the voltage source, right? And that one is around 10 volt. So due to that 10 volt voltage drop, we got 10 volt as the output, right? And if I change the resistance from 1k to 2k, you can see that the output voltage is changed from 10 to 13 volt, right? And if I change it to 10k, then you can see that it will change to 13 to 18 volt, right? That means if I change the load resistance from one value to another value, then you can see that the output voltage is changed, right? That means if I change the load current, then load voltage is also change, right? That means that the output voltage is not regulated. Okay. And also here I show you about the load current, right? Suppose I change the input voltage. Here you can see the input voltage is 20 volt, right? Now if I change the input voltage from 20 to 30 volt, then you can see that the output voltage is changed from 10 volt to 15 volt, right? And if I change to 40 volt, then output voltage is changed from the 15 volt to 20 volt. That means if I change the input voltage, the output voltage is also changed, right? That means this circuit is not working as a voltage regulator. Okay, so what we need to do? We need to connect a device such that this will act as a voltage regulator. Okay, and at that time, if we change the resistance, load resistance, and the input voltage, the output voltage should be constant. Okay, that device is the Zener diode. Okay, now let's go to this circuit. Here you can see this is the same circuit with the 1k and 10k resistance, right? But here I connect an additional device called Zener diode, okay? And you can see here the input is 20 volt, right? But the output you can see is 6 volt, okay? So now if I change the resistance from the 10k to 20k, you can see that the output voltage is still constant from 6.05 to 6.05, right? And if I change to 40k, then also you can see that the output voltage is around 6.05 volt. That means by changing the output resistance, the load voltage is the constant. That means is not varying that much, okay? And also if I decrease the resistance from 10k to 6k, then the voltage is around 6.05 volt, right? And if I change to 1k, at that time you can see it's 6.03 volt. Change a little bit. Okay. So that means if I varied the load resistance from 1 kilo ohm to 40 kilo ohm, the voltage change is around only 0.02 volt. Right? That means we can say that this voltage is regulated voltage. Okay. Where if I change the load resistance, the load voltage will be constant. Okay. This will be the load regulation. Now we need to check the line regulation. That means in this particular case, what we will do? We will change the input voltage and we will see that this circuit is work as a voltage regulator or not. Okay. Currently you can see in this circuit 20 volt is the input voltage. Okay. Now if I change to 30 volt, now you can see that the output voltage is keep 6.06 volt. Right. If I change to 40 volt, then also you can see that the output voltage is 6.08 volt, right? That means if I increase the voltage, then output voltage is not increased, right? Now, if I decrease the voltage to 10 volt, now you can see that the output voltage is dropped a lot, it's 5 volt. Why? When the input voltage is 10 volt, at that time you can see this is 1k, this is 1k, right? That means the output voltage is 5 volt. And if I need to turn on the Zener diode, the minimum voltage required at the output terminal should be Zener voltage or 6 volt. Okay, so the output voltage is only 5 volt. That means the Zener diode is turned off. When the Zener diode is turned off, this circuit will not work as a voltage regulator. Okay, so if we need the regulated voltage, at that time this Zener diode should be turned on. Okay, now if I change the input voltage from 10 to 20 volt, you can see that the Zener is on. Why? You can see that some current is flowing through the Zener diode and the output voltage is 6 volt constant. But if I change to 10 volt, you can see that the current flow through the Zener diode is 0 ampere. That means the Zener is turned off. this is all about the Zener diode as a voltage regulator. Okay, whenever you make a voltage regulator circuit, at that time you need to check two things. One is the line regulation. That means all the thing will be constant. You need to change the input voltage and you need to see the output voltage is change or not. Okay, and another is the load regulation. Load regulation means you only change the output current or the load current, and we will check the output voltage is constant or not. Okay, so if I need to check that one, you can see if this is the output voltage 5 volt, and if I check the current, you can see in the x-axis this is current and the y-axis is the voltage. Okay, so if I change the resistance, then you can see that the load current will change, right? And now you can see up to 40 milliampere, this circuit will act as a voltage regulator, and you can see that in the screen the output voltage is constant at 6 volt, right? From 0 to 14 ampere, this circuit will act as a voltage regulator. Okay, but when I decrease the resistance, at that time current will increase, right? At that time the current is more than 40 milliampere. So at that time what is happening? The generator will be turned off. Why? You can see here now this circuit is not act as a voltage regulator. Okay, and you can see current flow through the generator is zero. That means Zener is turned off. Okay, so you can see that this is the load regulation characteristics of this circuit. Okay, and if I do the same thing with the line regulation, that means the input voltage will be in the x-axis and the output voltage will be in the y-axis. So, and if I change the voltage, you can see that this is constant, right? After around 13 volt, this is kept constant, right? Around 6 volt output voltage. But if I decrease the voltage from the 13 volt to 10 volt to 0 volt, you can see that generator is turned off. Why? The Zener current is 0 ampere. Okay, so this is the line regulation. Okay, so this is the simulation part of this voltage regulator. Now I will explain you why this circuit will act as a voltage regulator and why we need a voltage regulator. Okay, so let's go to the theoretical part. In our last videos, I already covered transformer, rectifier and the capacitive filter, right? And also I did one video on the concept of the loading effect, right? And in that particular video, I already told you why we need a voltage regulator, right? If you didn't saw that video, please go and watch those videos. But here I just tell you in the brief. Suppose this is a linear and bilateral network, okay? This is load resistance RL, okay? Thevenin's theorem states that any linear bilateral network can be converted to a circuit consisting of a voltage source VTH with a series resistance RTH, okay, and a load resistance RL. Okay, we can convert this kind of circuit to this kind of circuit, right? That means this whole circuit we can convert it to a circuit where VTH and RTH is there, right? That means this RTH will not be the zero. Here we make a power supply, right? That means we got a voltage source with non-zero source resistance. Okay, so what will happen? The voltage at the load resistance will be VRL equal to RL by RL plus RTH into Vs, right? That means the output voltage VRL or the V0 is completely dependent upon the resistance value, right? And also, if I change the input voltage also, then also the output voltage is changed. That means the output is not regulated. Okay, this output voltage can be controlled by the change in input voltage as well as the change in resistance, right? So we need a voltage regulator such that if I change resistance, output resistance, the output voltage will be same. Okay, and also if I change the input voltage after some certain limit, then also output voltage will be changed. Okay, so this is the requirement of the voltage regulator. Okay, so you already saw that in this particular circuit RS and we have RL, and suppose this is a voltage source, which is okay, this is Vs and this one is the internal resistance of the voltage source with the Rs equal to non-zero. Okay, so we got V0 equal to RL by RL plus Rs into Vs. Okay, and I already told you this output voltage will vary by changing the RL and Vs, right? So what we need to do? We need to connect a Zener diode. Okay, when we did the previous year question of the Zener diode, at that time I already told you the characteristics of the Zener diode, right? In the forward bias, the Zener diode is same as the normal diode. Normal diode equal to Zener diode on the forward bias, okay, and this will be 0.7, okay. But in the reverse bias, the characteristics is different, okay. In normal diode, this is the avalanche breakdown, okay, where after the avalanche breakdown, the diode will be burned. We cannot use the diode, okay. But for the Zener diode, this point will be Zener breakdown. That means after the Zener breakdown, we can use this diode again. And this is the main important thing for the Zener diode. Okay. By using this concept of Zener breakdown, we can use this Zener diode as a voltage regulator. Why? You can see that after the Zener breakdown, the voltage is constant, right? That means if we change the input voltage, the output voltage will be the same. That means we got a regulated voltage. Okay, that's why we need a Zener diode to make a voltage regulator. Okay, so how does Zener diode act as a voltage regulator? Let's see. This is the input voltage Vi, right? And this is Rs and this is RL. Okay. So first what we need to do, we need to turn on this particular Zener diode, right? If we need to turn on the Zener diode, then what we need to do? Suppose the Zener diode voltage Vz is around 6 volt. Okay, suppose, assume. And this point is A, this point is B. Okay. If we need to turn on the Zener diode, then VAB should be greater than Vz should be greater than 6 volt. Okay. That means the VAB potential, if greater than the Zener breakdown voltage, then this generator will be turned on. Okay. So let's do the calculation when the generator will turn on. Suppose we assume that generator is off. Okay. If the generator is off, then the voltage VAB equal to RL plus RL by RS plus RL into VI, right? Now we can write down if VAB equal to RL by RS plus RL into VI greater than VZ, then what will happen? This generator will be turned on. Okay, and if this generator is turned on, after that, if you increase the voltage Vi or if you change the resistance RL, output voltage will be the same. Why? As Zener already reached the Zener breakdown potential. As if you change the resistance after that and if you change the voltage after that one, increase that one, then also generator will be turned on. Okay, and when the generator will turn on, this will be act as a voltage regulator. Okay, you understand the concept? Now there is also some limitation, right? As this is a Zener diode and there is some power limit of the Zener diode, right? Suppose you got a Zener diode with 6 volt and 0.24 watt power capacity, right? That means the maximum current I max will be 0.24 divided by 6 equal to how much? 40 milliampere. Okay, that means the maximum current generator can tolerate is the 40 milliampere. Okay, if the general current is more than 40 milliampere, then what will happen? This generator will be burned. Okay, and if this generator is burned, then we will not get this regulated voltage. Okay, when I solve the previous year question paper, I already show you some example where I show you that there is some limitation of the current, and due to that one, there is some range of the regulated voltage. Okay, so this is the main concept of the generator. Okay, now I already show you the minimum voltage criteria, right? That means when the VAB is just greater than VZ, the generator will turn on. This is the minimum criteria for the circuit turn on. Okay. Now, what will be the maximum voltage? Maximum input voltage generator can withstand, or the maximum load resistance generator can withstand. Okay. Suppose this RS is constant and the value of IS will be VI minus VZ divided by RS. Okay. You already got that one. As this potential is Vz. Okay. So we can write down IL will be Vz divided by RL. This will be the load current IL. Okay. So what will be the value of IZ? We can write down IZ will be IS minus of IL. Okay. Vi constant, Vz constant, and source resistance is constant. That means the value of IS is constant. Okay. And what you are doing? You are increasing the load resistance, right? If I increase the load resistance, then what will happen? IL will be low. What will happen? The more current will flow through the Zener diode, as IS is the constant. So if the IZ will increase due to the increase of the load resistance, then what will happen? We need to check if that particular IZ is more than the maximum Zener capacity current I max Z, then what will happen? Then Zener diode will be burned. Okay, it will be turned off. Okay, so from this concept, there is two concepts. One is the load regulation, one is the line regulation. Okay. Okay, so you can see what is load regulation, what is line regulation. First is the line regulation. Okay, here three parameters is there, right? One VI, another RS, and another is RL. Okay, when we will do the line regulation, at that time RL will be constant, RS will be constant, and we are dealing with the VI. So what we need to do? We need to check the output voltage V0 equal to VAB here. Okay, that one by changing the input voltage. Okay, so what type of curve we can see? We can see that first it will start from here, okay, increase the input voltage, and then after some time, what will happen? This will be constant, okay. In this particular point, V0 is just equal to Vz. That means here in this point, the Zener is turned on, okay, and then we got a regulated voltage. Okay, so this one is called the line regulation curve. In this particular time, all other parameters will be constant. Okay, and after some time, suppose this point, what will happen? The generator will be breakdown. That means it will be like this, as generator will be burned, and after the generator burned, we cannot use the generator anymore. And at that time, this curve will follow the voltage V0 will be RL by RL plus RL into VI. So this will be just a linear curve. Okay, this slope and this slope will be the same. Okay, this slope and this slope will be the same, though I in the drawing it will be a little bit different, but you remember this one. If this slope is m, this slope will be also the m, as here also the equation will be the same as this one. And in this particular timeline, the Zener diode will on and it will act as a voltage regulator. Okay, so in this particular circuit, this is the range of the input voltage where Zener diode will act as a voltage regulator. Okay, so in the exam maybe you can get some question where you need to see this kind of thing. Okay, how to get this point? This point you will get from this particular value. Okay, where you just need to equate this one with the Vz, then you can get this point. And how to get the maximum point? You need to calculate the Is, you need to calculate the Il, and you need to calculate the Iz. And Iz will be just equal to the Iz max. At that time, it will be give you this potential. After this particular voltage, this will be breakdown. Okay, so this is called the line regulation part. Okay, so this is the line regulation. Now go to the load regulation. So in the load regulation, we have three things, right? One is the VI, RS, and RL, right? So for the load regulation, VI will be constant, RS will be constant. What we need to do? We need to change the value of RL. Okay. If I change the value of RL, then what will happen? If RL will change, then load current will be changed. Okay. So what type of curve we can see? If this is the input voltage V0 and this is the load current IL, then the curve will be, this will be Vz. Okay, then the curve will be, looks like this one. Okay, and this point is the maximum current such that after this current, this circuit will not give you any regulated voltage. After that current, you can see this voltage will be decreased. Okay, and this circuit will not act as a voltage regulator. Okay, when the load current is zero, at that time you can understand all the current will go through the Zener diode and Zener diode is turned on. Okay, that means this will give you a Vz potential. Okay, that's why you can see is the constant. Okay, and in this particular point you are decreasing the load resistance. Okay, and if you decrease the load resistance, then what will happen? The potential across this Zener diode will be decreased. Okay, why? As VRL or V0 or VAB equal to RL by RL plus RS into VS, right? Here VS, RS is constant, right? That means if you decrease the RL, then VRL or V0 or the VAB will be decreased. And after some time, you got a condition where V0 equal to less than Vz in this particular point. That means after this point, here the generator is off. Okay, as the generator is off, then you will not get any regulated voltage. Okay, this will be the concept. Here what I did, you can see here I start from the zero current. Okay, here the source resistance will be such that when there is no load resistance at that time, if all the current is go to generator, generator should be okay, generator should not burn. Okay, we need to calculate source resistance such that generator can tolerate that particular current. Okay, if no, then generator will be burned. Okay, so this is all about the Zener diode and the line regulation and load regulation. Okay, so I already completed the whole power supply part, right? From the transformer, rectifier, filter, loading effect, and the Zener diode line regulation, load regulation. And for the problems, for the Zener diode load regulation, line regulation problem, I already have some video where I solved the Calcutta University previous exam papers. Okay, our next video will be on the regulated power supply by using two transistor. Okay, where you can see here the load current will be maximum of 100 milliampere, not more than that. After the 100 milliampere, you can see that here we don't have the regulated voltage. Okay, so we need a power supply with the higher current, or suppose 1 or 2 ampere current. Okay, what we need to do, we need to use a power transistor. Okay, so at that time we need to use two transistor and one Zener diode to make a voltage regulator such that our output voltage and output current will be range will be higher than this one. Okay, so that's all for today. See you in the next video. Okay, thank you, bye bye. Thanks for your time. Please do share this concept with your friends, and if you like this video, please press the like button. It is really means a lot for me. Bye bye. L plus Rs into Vs, right? Here Vs, Rs is constant, right? That means if you decrease the RL, then VRL or V0 or the VAB will be decreased. And after some time, you got a condition where V0 equal to less than Vz in this particular point. That means after this point, here the generator is off. Okay, as the generator is off, then you will not get any regulated voltage. Okay, this will be the concept. Here what I did, you can see here I start from the zero current. Okay, here the source resistance will be such that when there is no load resistance at that time, if all the current is go to generator, generator should be okay, generator should not burn. Okay, we need to calculate source resistance such that generator can tolerate that particular current. Okay, if no, then generator will be burned. Okay, so this is all about the Zener diode and the line regulation and load regulation. Okay, so I already completed the whole power supply part, right? From the transformer, rectifier, filter, loading effect, and the Zener diode line regulation, load regulation. And for the problems, for the Zener diode load regulation, line regulation problem, I already have some video where I solved the Calcutta University previous exam papers. Okay, our next video will be on the regulated power supply by using two transistor. Okay, where you can see here the load current will be maximum of 100 milliampere, not more than that. After the 100 milliampere, you can see that here we don't have the regulated voltage. Okay, so we need a power supply with the higher current, or suppose 1 or 2 ampere current. Okay, what we need to do, we need to use a power transistor. Okay, so at that time we need to use two transistor and one Zener diode to make a voltage regulator such that our output voltage and output current will be range will be higher than this one. Okay, so that's all for today. See you in the next video. Okay, thank you, bye bye. Thanks for your time. Please do share this concept with your friends, and if you like this video, please press the like button. It is really means a lot for me. Bye bye.